Okay, so let's start column generation in machine learning. This essentially falls in the area of operation research and machine learning. So the idea is that machine learning has a lot of heuristics, and we want to use operation research techniques to improve upon those heuristics. Okay, so today particularly we'll be focusing on column generation, which is the technique that we use for solving linear program with very large number of variables. When I started my PhD, I didn't have a lot of background in either column generation or in machine learning. I knew what those two fields were, but I never really used them in practice. So for me to do a PhD on this and contribute to human knowledge and everything, it's kind of pretty hard thing to do. It is in fact as hard as playing this position with white. So just to give you a context, it's first of all white to move, and black is up couple of rooks and a bishop, and is threatening checkmate in the next move. So pretty hard position for white to play. Lots of threats and very little material. So in this kind of position, the best thing to do is to get started, and that's what we did. Sanjeev Das and others came up with a nice way of generating Boolean decision rules using column generation. And we wanted to use that method in some real world setting. So that's what we did. Initially, the goal was not really to publish a paper, but it was more about me getting started in doing column generation for machine learning. And the idea was that eventually we will face some challenges and get to learn about column generation and machine learning, and we'll hopefully get some ideas for the future projects as well. That's why we basically started this project, and it turns out that we provided explainable predictions without losing a lot of accuracies, and this was the first time we were actually using Sanjay Das method in a real world scenario. So that's why all of that work was publishable, and all of that work is in this paper, which is published in Journal of Operational Research Society in 2023. Okay, so let's talk a little bit more about that work. So in particularly, I'll be talking about what are Boolean decision rules, what are NOTAMs, and what are the major issues that are that we faced for applying Boolean decision rules in NOTAM application. Okay, so let's start with Boolean decision rules. So Boolean decision rules look something like this. They are essentially ORs of ANDs. So these X are my binary features of the data sets, and everything that is in this parenthesis are called clauses. So in Sanjeev Das model, there was one variable for every possible clause, and these are the variables that are exponentially many, and therefore they are actually generated using column generation. I'm not going to go into details about how they are generated because the other parts are rather more interesting. The thing is that for this Boolean decision rule to be satisfied, or rather to predict as a true answer, one of these clauses have to be satisfied, right? So, and there can be like more than three clauses, and there can be of course bigger clauses and everything. But so that's the key idea, that one of these three clauses or multiple clauses has to be satisfied, and therefore they are explainable classifiers. So once something is classified as true or positive, then we know that which clause was responsible for that true prediction, and therefore like we can say that this input is classified as true or positive because this features were on, right? So that's the biggest advantage of this Boolean decision rules. Now let's talk about the application that we are going to use that in, right? So that application is NOTAM. So what is NOTAM? NOTAMs are essentially text messages like this. So they look like teenagers are texting, but they are actually important flight route related information. Yeah, so they are essentially read by airline pilots, and only some of them are important, right? So not all of them are important at all points of time, and pilots have a lot of other things to do, like flying a plane and everything. So in order to help pilots, essentially this NOTAMs are assigned something called a label, which is called a Q code. That basically looks like that. Okay, so our goal is to, given this kind of a text message, we want to predict this Q code. According to Thales, we had to do it in an explainable way. So that's why we decided to give this Boolean decision rules a try. We want to see how explainable they are, and also how much are we losing in terms of accuracy when we move from standard classifiers like neural networks and other to this kind of explainable classifier, right? So that's why we decided to give it a try. And now let's talk about the major issues that we faced, and most of those issues were related to multi-class extension, right? So we had a lot of different Q codes, right? So in my data set, there were already 600 plus Q codes, and there were more possible Q codes. Whereas this Boolean distant rules can only output true or false. It's essentially a binary classifier, and we have to extend it to this multi-class setting. And that's not really a challenge. I mean, it's kind of solved in machine learning community. It's called one versus rest. So the idea is that we train one classifier for each class in our data set, and that classifier will only tell me whether this input belongs to their particular class or not. They will not tell me about what happens to the other classes. Okay, so that's the one versus rest technique that's already known, but there are issues even after that. So let's talk about these two particular issues that were the major issues in my case. So let's start with this class imbalance. Okay, initially Sanjeev Das designed this column generation based algorithm to create Boolean distant rules, and that entire method was designed for this balanced kind of classes, right? So where positive and negative data points are roughly equal in number. So first of all, this is like the ideal case scenario in machine learning tasks. Let's say if we have this ideal case scenario in our case where we have multi-class extension, where I have one classifier for each class. So the positive examples come from only one class and negative examples come from all the other classes. So even if all the classes have roughly equal number of data points, we are still in this kind of inherent imbalance scenario, right? So the number of negative examples are just way too many, and therefore they just outweighed the number of positive examples, and therefore a lot of positive examples kept getting classified as negative ones. So in order to fix that, the fix was very simple. It's just that we had to introduce a weight for the positive misclassification penalty. So in other words, like every time we misclassify a positive example as negative, we would want to punish it more. And that's the only small change in the master problem objective that we made, and that roughly fixed that issue. Okay. So the second issue, let's talk about the bigger issue, which was tie breaking in one versus rest. So let me first describe what that issue is, right? So let's say we have this one versus rest setting. We have this many different classifiers, this many different classes, one classifier for every class, right? So once we give one input, let's say three of them say that this input belongs to my class. So how do we decide like which is the real class? And this issue is also not new. Support vector machine, for example, is another binary classifier that has been successfully extended to multi-class setting. So how they solve this issue is by using a distance function. So they not only tell me that this input belongs to my class, but they also tell me that how confident am I about this input belonging to my class. And we don't have that, right? So we have a Boolean distant rule that can either output true or false. So they don't give you a number in the sense that how confident we are about that classification. So we wanted to fix that. We wanted to design some sort of a distance function. So let's try to design one. Okay. So our Boolean distant rule has basically this kind of clauses. I decided to create some sorts of weights for each and every clause. Okay. So I measured the accuracy of this clause on positive and negative data sets. So for positive data set, what fraction of the positive data points that I have are satisfying that one particular clause, right? And so that's the positive accuracy, let's say. And same thing for the negative examples as well. Like, so what fraction of my negative examples are satisfying that clause? So obviously we want positive examples to satisfy that clause and negative example to fail that clause. So I just took the simple combination, which is by taking the difference from positive and negative accuracy, and that is the weight of a clause. Okay, so now that we have weights of a clause, and we know that every time an input is classified as positive, it has to satisfy one or more clauses. So let's say it satisfy two clauses like this, then what I will do is I'll just simply add up the weights of these two clauses and call that as my weight for that input. So this is not on a particular scale or something, but it roughly represents how confident am I about this input belonging to my class, right? So it can be like bigger than one and everything, but it still represents what I can use for tie breaking. Okay, so these were the major ML related issues. Now let's talk about column generation related issues. Okay, so essentially that's why we started this project, right? So we wanted to learn more things about column generation. The biggest issue with column generation is the training time. So column generation is an expensive process, and training times are therefore very, very high. Like it takes a lot of time to finish the training. So there are many ways in which we can address that training time issue. So one of them is called by using initial columns. The idea is that we don't have to generate all the columns, so using that column generation process. So some of these columns we can just directly put at the beginning in the master problem, and those we can just simply reduce that many number of iterations. So for this project I didn't do anything about initialization. So now looking back at I can think that there are smarter ways of doing initializations. I could have used some of these clauses as initial columns, but for this project I didn't do anything. So if you are interested, we can talk about it at the end, what all things can be done about initialization in this project. And the other way of speeding up the training was improving the subproblem speed. Right. So in our logs, we saw that about 95% of the training time was essentially consumed in solving the subproblems, the way we generate the columns essentially. Right. So subproblem speed was essentially the real bottleneck over there. So I did 3 different things to work on that. So let me describe them quickly. So first was heuristics. That is, like, I generated all the smaller size clauses using brute force. So if that the clause has negative reduce cost, I wouldn't really trigger the integer program. The second one was that I could find that some variables I could fix, and that would chop off some feasible region, but that feasible region would not have any solution with negative reduced cost. I mean, it was safe to chop off that feasible region, and therefore, that way I can make the solver's life slightly easier. And finally, we tried a faster solver, which is like CP-SAT solver instead of Gurobi. It has nothing to do much with constraint programming in general, but it is more to do with how the solver is architectured. So it usually works better when you have a lot of binary variables and problem is more combinatorial in nature. So that's what also kind of help with the subproblem speed. Okay, so now let's talk about the results, how we are doing. So compared to the neural networks and support vector machines and other state-of-the-art classifiers, we are not as good. But if we look at the top 3 to 5 predictions, then we are in a comparable range with standard SVM type of classifier and 4-layer neural networks and everything. And the key advantage is that Boolean decision rules also give explanations with their classification, right? So the neural networks, SVM, and other classifiers cannot really provide you any explanation. So here we can say that this NOTAM is assigned this Q code because it contains this and this words, whereas the other classifiers can't. So yeah, overall it's like we could gain explanations without losing too much in accuracy. So overall decent results. Right, so that's the end of the first project. Now let's go back to the chessboard, and we want to get started on this. So chess experts in this kind of positions give a simple advice, which is look for checks, captures, and attacks in this order. So we are going to look for checks first, and notice that the black king and the white queen are in the same diagonal. So anywhere we move the knight, it is going to be a check. So we are going to move this knight to this h6 square. So that way it is going to be a double check, right? So it's a check by the queen and also the check by the knight. So it's a double check. It cannot be blocked. The king has to move, and king, let's say, moves to this corner because the other square is covered by the bishop. That basically brings us to the second project, which is follow-up. So we gave a nice check, but we still have to follow up on that, right? So, and speaking of follow-up, a nice follow-up for Boolean decision rules is decision trees. So they're structurally very, very similar. And since we could apply column generation for Boolean decision rules, it should not be a surprise that we can also find an application of column generation in decision trees, right? So we came up, we came across this paper by Firat and others that proposed a column generation based heuristic for learning classification trees. And we improved upon their heuristic. So our work is published in this paper, which is an improved column generation based heuristic in learning classification trees. Classification trees or decision trees, basically the same thing. And this work is published in Computers and Operation Research and in this year itself, right? So let's talk about that work a little bit more. So these are the kind of decision trees we are looking at. It has a bunch of internal nodes and bunch of leaf nodes. So the internal nodes have questions in them, which are certain feature of the data set is less than certain threshold. That's the format. We'll call these questions split checks. And the leaf nodes have targets in them, right? So particularly in this example, we have 2 targets, rights and wrongs. We can have more than two targets. It's not necessarily a binary classifier. And the goal is that we want to decide what should be the split checks in the internal nodes and what should be the targets in the leaf nodes. And there are many ways in which we can decide them. So particularly, we have two things at our disposal. So on one hand, we have CART algorithm, which is typically used in machine learning. It's very, very fast, very, very scalable. It works on a very large number of data sets and everything, but it's not optimal. The thing is that it only looks at one layer at a time, and it therefore cannot really prove optimality of the descent tree. It doesn't matter how you define optimality, it simply cannot achieve optimality. It's a heuristic basically. And on the other hand, we have OR techniques like mixed integer programming, CP and SAT models. And sometimes these models can provide optimality guarantees and provide optimal descent trees. But the thing is that they are not scalable. So Firat and others showed that these models were basically failing after 10,000 data points. Like if you have data sets which have more than 10,000 data points, then these methods won't work. So that's why they decided to come up with something in between, which is a heuristic, not something that can prove optimality, but something that is also closer to optimal and more scalable than these OR methods and more optimal than the CART method, right? So that's what they came up with. So let's see what they did. So first, let's talk about why it's a heuristic, why it's not, why it cannot provide optimality guarantees. It's because they don't consider all possible split checks. So there are many possible split checks for each and every internal node. And they said that we are not going to look at all possible split checks. We'll only consider some small candidate subset of that split check. And out of that, we'll decide which one is the best one, right? So let's see how that candidate set is created. So let's say we have a data set. So what they did was they basically selected a small random portion of this data set. They'll give it to CART, and CART will generate a descent tree using its, it's very fast, so it doesn't take a lot of time. And whatever CART has generated, they will just simply add those corresponding split checks to these corresponding nodes in their candidate sets. And they just simply repeat this process multiple times, and that's how they generate this candidate sets. And they, at the end, they'll basically keep the most frequent split checks and throw away rest of them. All right, so that's how they basically came up with these candidate sets. And now the problem is that we want to decide which one of these candidates to select for the internal nodes and what should be the target that should be selected for the leaf node. So for that, they used the column generation. Now first consider this path from root node to leaf node with one specific split check assigned to each internal node and a specific target assigned to the leaf node. And for that path, they created one binary variable. And so the goal is that they want to decide whether this path is present in my final descent tree or not. And this are, since there are exponentially many variables, so like just for the highlighted nodes, there are 12 possible choices, right? So 3 choices at root node, 2 choices at the middle node, and 2 target choices at the leaf node. So it's essentially 12 choices in just the highlighted nodes. And there are many other nodes. And if you consider even bigger trees, then there are just way too many path variables. So these are the variables that are essentially generated using column generation. Okay, so let's now take a look at the master problem. So the constraints and everything else is essentially formed around these variables, but I'm not going to describe the mathematical formulas for those constraints. Okay, so let's start with the master problem. Okay, so the first constraint is that for every leaf, exactly one path with this leaf should be selected, right? So just for the highlighted nodes, we saw that was one leaf, and for just that leaf, there were 12 possible paths in the previous example. So out of those 12, we have to select only one of them. So that's the first constraint. The second constraint is on the input data rows. We have one input that can satisfy multiple different paths, but there are too many possible paths. So it should be not surprised that one row can satisfy multiple different paths. And out of those multiple satisfied paths, we have to select exactly one of them. So that's the second constraint. The third and the last constraint is that for any, so once we have one path selected for every leaf, so they have some common nodes in between, and the idea is that those paths that we have selected should agree on the common nodes, right? So they should basically have the same split check assigned for that common node. So internally, the tree should be consistent. And so these are all the constraints, and the objective is simple. It's like just maximize the training data accuracy. And that's a very simple objective. There are more complex objectives that are present in the literature, and that also can be used in this model. But Firat decided to consider very simple objective, which is maximizing training accuracy. And so we are also going to use that same objective. Okay. So that was master problem. Now let's take a look at how those path variables are generated. So trick is very simple. Like the way we do things in column generation is that we take a look at the master problem, take the dual cost, compute the reduced cost expression, and then optimize that reduced cost expression. Right. So in this case, we are maximizing. So we are going to maximize that reduced cost, and the constraints are just basically ensuring that the accuracy is properly computed. So I haven't described the constraints in detail because for this presentation, they are not that important. The key point to remember is that all of these constraints are linear, and even in the master problem, whatever the constraints I just discussed, they are all linear constraints. So we are still in a linear program slash mixed integer program, mixed integer linear program setting. Right. So the important thing to notice about this subproblem is that there is one subproblem for each leaf and each target. Right. So for this example, there are 4 leaves and 2 possible targets. So there are 8 subproblems. And that's where our first contribution comes into the picture, where we decided to move this target computation inside the constraints. So now there is one subproblem for every leaf. So for this same example, now instead of 8 subproblems, we have only 4 subproblems. Of course, the subproblems are bigger in terms of number of variables and number of constraints, but the number of subproblems themselves have reduced by 2-fold. Right? And if you have more than 2 targets, then it can be reduced by multiple folds as well. And so experimentally, this was very beneficial. So that was our first contribution. The second contribution came again from the master problem. If you look at carefully at this master problem, then you'll realize that this beta constraints are essentially not needed. So in other words, like if you have one path selected for every leaf, and all of these selected paths are consistent with each other, they have the same split checks at the different nodes, and you have maximized the training set accuracy, then the given row will only satisfy one path that is selected, because it will eventually land to only one leaf. The tree is properly well defined by these alpha and gamma constraints, and only one, for every leaf you have only selected one path. So therefore these beta constraints are by default anyways satisfied. So that was our understanding, and we decided to remove these beta constraints. So it turns out that in theory, yes, they are satisfied, and therefore they should not be needed. But our master problem, that we solve the master problem using column generation. So we solve master problem as the linear program and using simplex method and everything. So it turns out that without this beta constraint, the relaxation quality is very, very bad. And therefore, eventually, if we don't use full branch and price, it degrades in terms of accuracy, right? So we decided to instead not completely discard it, but started using them as cutting planes. So the idea is that we will not initially have any of these beta constraints, but if they are violated by the relaxation, then we will add them to our master problem. That's the thing that really worked well for in terms of training time and accuracy overall. Like, so that's the best balance. But this beta constraints, they depend on the data set that is given to us, right? So what if there is a beta constraint for which there is no corresponding row in our data set? Can we generate them? That's what we try to do. So it turns out that since these beta constraints are not using the target information, so we can actually generate rows, artificial rows in our data set, which has no target at all. And the idea is that the corresponding beta constraint for that row will be violated. Right? So this beta constraints only enforce that the path should be satisfied by the row, in the sense that it should be followed by the row. They may have different targets. Okay. So in order to create that, we just simply used a SAT model, which was basically maximizing the violation of this beta constraint, and it was basically deciding what that generated row will do on each and every different split check. That's how we did things. It was still slower in practice, but it had some theoretical importances. If you want, again, like we can talk about this during Q&A. Right, so that's the contribution on the master problem. And this time we also worked a little bit on the initialization. So recall that process of generating candidates while using those cart iterations. Firat used those cart iterations to generate those candidate sets. We also use that for generating initial columns. So whatever cart was generating, we thought that these are all very good, high quality initial columns, initial paths. So we can just simply add them to the master problem at the beginning, and that actually brought up some benefits. And of course, like we did some more heuristics as well. So overall, the work was kind of everything basically worked out well and brought some benefits. So the numbers are over here. So these are the training accuracies on the small data sets which have more than 500 data points but less than 1000 data points. And yeah, I mean, compared to cart, basically both the algorithms are doing better. Both the column generation algorithms are doing better, and compared to Firat, we are slightly better, but the improvement is consistent. It kind of worked out. So for the larger data set, Firat basically did not report the accuracies on the training data sets. So we had no choice but to compare the accuracies on the testing data set. So recall that Firat did not really focused on generalizing the performance for the testing data set, and we also consider the same objective. That's why you see a lot of zeros in the gain columns for both these algorithms. But even in this case, we are still either similar or slightly better than Firat, right? So for example, if you look at the letter recognition, so over there we are improving 2% or 3% in the testing accuracies as well, right? So it is still beneficial. And of course, like the entire model can be made to work with generalization in mind. Yeah, that's essentially all the work for the second project, decision tree project. And now let's go back to the chessboard again. So we have to follow things up, right? So for this, what we are going to do is we are going to move our queen right next to the king. So king cannot really move anywhere, and king cannot really even take this white queen because the white queen is guarded by the knight. The rook can. So rook basically takes the queen, and we lose our most important piece. So I mean, at this point of time, we can give up, or we can say that was the plan from the beginning, right? So the thing is that we know that we made a blunder, but our opponent doesn't know that, so we can always keep them in doubt. And okay, well, that's not why I decided to give this title to this project. This third project was essentially running right from the beginning of my PhD. So the idea was that Andrea basically figured out that I'll be working on a lot of column generation based classifiers. So he said, like, why not create a simple framework for that? So that's the third project. Uh, so there are multiple advantages. So one is that I don't have to repeat a lot of my work, and second advantage is that this entire framework is built on top of scikit-learn. So if you don't know, scikit-learn is a very famous library, Python library for machine learning. It has support for all the tools that you might need for machine learning, starting from pre-processing, cleaning, splitting, anything that you want to do, including hyperparameter tuning, and you can even build entire pipelines in scikit-learn. So very widely used and very famous Python library. And the idea is that if we make a classifier that is compatible to scikit-learn, then it has more chances of actually being used in practice. So that's why we decided to build our framework on top of scikit-learn. And compare and in the if you look at from the developers perspective, they also get a lot of advantages in the sense that they only have to now worry about the implementation of master problem and sub problem in their favorite solver. Of course, all the column generation part and the scikit-learn part, integration part, is taken care of by the framework itself, right? So the framework basically keeps track of important metrics, and it maintains all this. It does basically all this column generation loop and termination criteria. Everything is essentially taken care of by the framework, right? So particularly, this framework can also be used for solving some of these common problems that we face in using column generation based classifier for scikit-learn. So one of those problems is doing something better than restricted master heuristic. So restricted master heuristic is essentially using column generation at the root node, and whatever columns have been generated, use those columns for solving the integer master problem. But and basically not to use full branching price, but we can do better things than that restricted master heuristic, which is we can essentially do some sort of diving algorithms, and all of that work can be implemented in this framework itself. And so we decided to handle a different problem. So we focused a lot on sub problem. So why we focused on sub problem is because, like, for the first project, as I said, it was taking about 95% of the time. And second project also, we saw similar numbers. The sub problems were essentially taking 96% of the training time. So clear bottleneck. And That's why we decided to do something about it. So master problem and sub problem are very very similar to each other across different iterations, right? So master problem doesn't change a lot across different iterations, and sub problem doesn't change a lot across different iterations. So master problem only changes by additional variables. We just simply add a few columns every time if it at every iteration. And in sub problem, we only modify the objective. The rest of the sub problems remains as it is, if we are not using cuts, of course. But yeah, so that the thing is that master problem is solved using simplex algorithm, and it has inbuilt mechanisms of warm starting. So you don't have to start from the scratch when you are going for when you want to solve the master problem in the next iteration. You can reuse the solutions that was generated in the previous iteration and go from that. Whereas for the sub problems, we are solving them using integer programs, and for that there are not a lot of known techniques for warm starting. So that's a kind of a bottleneck, and that's kind of an issue. And the MIP workshop, computational competition in 2023, that basically focused on this particular issue, which is we want to solve integer programs that are very very similar to each other, that maybe only change in one component, let's say either the objective, or let's say the right hand side, or just the bounds, and otherwise they are essentially similar. Other components are similar to the previous iteration that we solved. So we just want to reuse the information that we have generated using by solving those previous instances, and in order to solve this current instance faster. So obviously I participated in that competition, and good things happened. So yeah, I won the competition. So from the beginning of my PhD, I always had this kind of a dream that I would want to win some award during my PhD. And so in a way you can also say that this is also the plan from the beginning. This was also the plan from the beginning. But well, not exactly this plan, but yeah, I mean, you get the idea, right? It's a high level plan, you can say. Well, let's now talk about what all things I did for this competition. Some of this work is already being used in the framework itself. So my work is in this paper, which is at this point of time accepted for publication in Math Programming Computation, and will soon be published in MPC journal. But if you are interested, you can you can find this paper in arXiv. So let me quickly describe what all things I worked on. So I worked on majorly 4 different techniques. So the first one is about improving the primal bound faster, and the other 3 techniques focus more on improving either the dual bound faster or improving the solver configuration. Okay, so for the primal bound improving faster, turns out that giving the previous instance solution as it is doesn't work. So what I did was I essentially combined the sum of previous instance solutions and took out their common parts and gave that common part as a partial hint to the solver, and let that solver complete that partial hint to basically figure out what should be a feasible solution. So that is the thing that really worked out well. But still, like, the primal side improvements had limited impact in terms of overall solving speed. The major impact came from the dual bound improvements, which are the other 3 techniques. So reusing pseudocost is that pseudocost essentially are ways of measuring how good a variable is for branching. Initially, they are all zeros, and as we explore the tree, we get more and more training data, and we figure out how good a particular variable is for branching. And basically, the idea was that after solving few instances, we don't have to start from zeros. We can reuse the pseudocost that were generated in the previous instances, because the future instances are going to be similar to that instance, right? So this similar idea was basically for using extra strong branching. The idea is that initially pseudocosts are 0, and in order to speed up their collecting the pseudocost data, we can sometimes use strong branching at the beginning. Of course, the branching distance at the top node are also very important. So pseudocost having 0 are highly unreliable. That doesn't work out well. So if we just simply extend this idea about using strong branching to initialize pseudocost faster. So I solved entire first instance using strong branching. Very controversial, of course. The idea is that, of course, I'm going to lose performance in the first instance, but since I'm reusing those pseudocost, and since I trained those pseudocost using strong branching, they are better trained and everything, so they are stronger pseudocosts. So therefore, it will benefit me more in the later instances. So that's essentially what ended up happening. The last technique was automated parameter tuning. So MIP solvers have a lot of components, a lot of parameters, and the default parameters are not the ideal ones for any given specific instance or given series of family of instances. So for that, the parameter settings differ, and we wanted to learn this parameter tuning online using reinforcement learning, simple reinforcement learning techniques. And we just wanted to try out a few things in the beginning and then figure out what works and then use that whatever was working at the for the later instances. So that is the thing that worked out really well. Okay, so let's talk about the numbers. The total score is essentially made up of two parts: how much time I consumed out of the given time limit, and what was the relative gap at the end. So lower total scores are better. So for the first batch, first 1 to 10 instances, the improvement is negative, or in other words, it's performance degradation rather, because again, like I'm doing a lot of exploration in terms of parameters and doing strong branching and everything. Therefore, obviously, I'm supposed to degrade in the first initial instances, and as we move to the later instances, the exploration starts slowing down and exploitation begins, and that's when we start seeing a lot of improvement. So it goes in the last batch up to 22% improvements in solving times. Okay, so in the total score, in fact, in general, right? So let's now talk about individual techniques. So the other techniques, primal solution and reusing the pseudo cost and branching history and strong branching and everything, all of those brought reasonable speed up to 1 to 2% speed ups. And the biggest speed up came from this parameter tuning, which was about 4% improvement. And the other optimization was also some sort of parameter tuning. It was basically like I will detect the statistics for certain pre-solvers, cuts and heuristics, and detect that some of them are not working well, then I'll just turn them off, right? So it's still like parameter tuning, but it's happening only in one direction. So parameter tuning, again, like, is the technique that worked out very well. So that's the one that we decided to start with when we want to implement all of these techniques in the framework. So we have implemented that parameter tuning technique in the framework project, and it is already bringing up to 1 to 3% speed ups. So it's a different solver, different parameters and everything, but still bringing those speed ups. Unfortunately, this speed up is not enough to be translated into accuracy. So we still need a lot more speed up in some problems to get better accuracies, but that's still like a work in progress. So there are still, like, we can do a lot more things, like implement all these other techniques and everything. So we are still hopeful about it. Right, so let's quickly conclude the talk. I'm going to use levels of learning for my conclusion. So the title for this PhD is column generation in machine learning. So the first level is, of course, knowing what column generation in machine learning means. So very easy, very trivial level. I'm not even going to talk about it. So the second level is knowing about where column generation has already been applied in machine learning. So I already described Boolean descent rules and descent trees, but other than that, column generation is also used in support vector machines and in boosting as well. And apart from the classifier settings, it's also applied in computer vision and applications where we can generate counterfactual explanations for neural networks and support vector machines. So all of those cases are usages of column generation in machine learning. So more details are there in the literature review chapter of my thesis. The level 3 is where the active learning starts, where we do things. So that's the level 3 is essentially applying existing column generation based ML classifier in practice. That's essentially the NOTAM project. Level 4 is modifying existing column generation based classifier. So that's the descent tree work, where not only it's just applying as it is, it's not enough. So we are now also modifying the master problem and sub problem and a few things in the training process as well. So level 5 is something that I didn't do. It is essentially now creating a completely new column generation based classifier or a completely new column generation based application. So I had some ideas in my mind when I started my PhD. So the thing is that it kept getting deprioritized because the other projects were more interesting, and the other reason is that because of this next level, which is level 6, which is create. It is essentially same as level 5, except that the new column generation based classifier also has to be useful, right? So just because I know column generation doesn't mean I have to push it everywhere. And the idea that I had in my mind, it after talking to a few people, it felt like it might not be as useful. So we don't know for sure, but that's the reason that I felt that it is not something that I would want to work on, because it has lower probability of being actually being useful, right? So that's the levels of learning. And since I didn't satisfy level 5 and level 6, to make up for that, I worked on this framework project, which essentially proposes solutions for the common issues that are faced in building column generation based ML classifier. So the framework project and the reoptimization work essentially falls in this criteria. So yeah, I think that's essentially the end of the presentation. Going back to the chessboard, we lost our queen, but if we move the knight to f7 square over here, then it's a checkmate, so white wins. And that was also the plan from the beginning. So that's the end of the presentation, and now it's time for questions. So